This is 7.1, day 1, properties of rational functions. So we're going to talk about graphing and a few things about that. But before we do that, these notes that I'm going to use are guided notes. The first few pages are not actually in the guided notes. So yeah, you can find the guided notes in the link, but for right now, just take a look at this. So I have a graph right here, and you can see it's labeled. No title though, but we have an X and Y axis labeled, and not a normal linear graph or quadratic graph that we're used to graphing. But I just want you to kind of soak this in and tell me everything, well, just tell the computer everything you know about this graph. Alright, so a little bit not too exciting, not too happy, but this is incarcerated Americans. So from 1920 to 2014, we've had a lot, I mean, from 1980 on, we've had a lot more people incarcerated. And there's probably many reasons, right? I mean, more people have cars, more people have internet, more people have, access to these things that are going to get us in trouble. So maybe not what you thought when you first saw this graph, right? That I was going to jump to people in prison or jail. But graphs obviously tell a story, and there's a lot, like I brought up, that we don't know about, that we'd have to go investigate to find out more about this graph. Now, same thing here. So our x-axis is not labeled, but it basically goes in time, I'll tell you that. So as time passes, something happens, superior, excellent, average, poor, or ignorant. What do you think's going on here? So this previous one was a real graph. This one is not. This one I just found, and I think it is maybe true sometimes, right? So you study for the driver's ed test, you pass it, you know all the rules about driving, and then you get on the road, and suddenly it's kind of like, who cares about rules? I mean, as long as you're not getting pulled over or running into people. And then how about this one? This is classic, like 7th, 8th grade math when we look at this. So the story that this tells, if you remember, y equals mx plus b. So if we take a look at our slope, we go up 1 over 1. So y equals x, our slope is 1, and our y-intercept's 3. So this tells a story as you plug in x's. So if we plug in a 0, we'll be at 3. If we plug in 0.01, we'll be at 3.01, right? So x and y. If we plug in a 5, we're going to be at 8. So these are the more graphs that we use in school. Not too exciting. But right here, let's pretend that I'm playing basketball. The green are the ones that I make. So I make 3 out of 16. Not too great right now. And I want you to kind of think about this. If we were to graph it, and I wanted to see how many makes. So if I make every next shot, right, because these are going to be the same, could I ever get to 100%? Just kind of think about this graph. So I made 3 out of 16 originally. So if I never miss again, so I shoot over here, I make. So that would increase by 1, increase by 1. So we'd have 4 over 17, right? I make this one. Now we have 5 over 16 plus 2, 5 over 18, right? So as I increase my x, so I'm saying I never miss again, just kind of think, what can I go to? Where will I head? Okay. And this graph would actually look something like this. Okay. So as I try to get to 100%, actually I'll never, ever, ever, ever get to 100%, right? Because I can never close that gap. No matter how I good am after this point, I can never get to that point. And this is an interesting topic that we're going to discuss, is when we work with fractions, when we work with rationals, sometimes they have limits that we call asymptotes, that they are points that they can never reach because of how functions that are fractions work. So this is just a normal rational function y equals 1 over x. And so you can see the x value, there's no way x can ever become 0, right? So the graph will never touch 0, never, ever, ever, ever. And the y-axis also, right? Because if I plug in a negative number, right? 1 divided by negative 1, I get 1, negative 1, right? Negative 1, negative 1. If I plug that in, the answer was negative 1. Okay, so just kind of think about that, but the point is, with fractions, the graph is going to tell a story, and that's our job, is to figure out what story this graph is going to tell. All right, so here's a look at what you have to look forward to. We're going to spend 2 days on 7.1, so all this week, basically. And then next week, we'll do 7.2, 7.3. You actually don't have a test, you have a project. If you're online, you'll be doing this project on your own, unless you have a buddy that you'd like me to assign you with, and you can work on it that way, but just a heads up there. All right, so rational graph properties, day 1. So a few things that we have to learn today. We're going to introduce you to rational functions. Remember, these are fractions. So everything we work with today will be a fraction with, and it's called rational because it is rational, but also there are x's in the denominator or numerator. Visualize how the excluded values, remember this is what x could not be, affect the graph. We're going to talk about holes versus an asymptote, and these are basically where x never goes, okay, for the most part. We're going to talk about discontinuity, so when a graph is not continuous. Discontinuity, continuous. So if you think of if they discontinue a product you like, they don't continue that, so dis means not, right? So not continuous. We're going to learn about x-intercepts, y-intercepts, and then talk about domain. So that's what we are doing. All right, so first take a look at this paragraph. A rational function is a ratio. So remember, that's a fraction of polynomial functions. If a function has a polynomial in its denominator, its graph has a gap. So think about it. If a function has a polynomial in its denominator, its graph has a gap at each 0 of the polynomial. So remember, in our denominator, if we got these excluded values, our calculator said error. There's no answer. So when we try to graph this, there's not going to be a y that lines up with that x. So we have a little gap. This gap could be a 1-point hole. Sometimes it's just a hole. Or it could be like a whole line, basically, and we'll talk about that. Or it could be the location of a vertical asymptote. And an asymptote is kind of like a gap in the graph, but the graph will basically follow that, and I'll explain that in a second. All right, rational functions may have no asymptotes. It's possible that there's no gaps. They may have one horizontal or oblique. So vertical up and down, horizontal left to right asymptotes, and any number of vertical asymptotes. It could have many, okay? All right, so going back just real quick to this graph. So an asymptote is basically an imaginary line on a graph that the graph's going to get really close to but never touch, okay? All right, so 1 over x is never going to go to 0, right? There's no way it can become 0. If we try to plug 0, it just becomes undefined, okay? So the answer can never, ever, ever become 0, as you can see, okay? Also, we can never plug in a 0, because if we do try to plug into 0, it'll say error, right? We can't divide by 0. So we have a vertical and a horizontal asymptote here. Let's think about this one here that I was talking about. So if I start out the season making 3 shots out of 16, if I never missed a shot again, I could never get to 100%. So it's kind of like a cap. So an asymptote is like something that the graph's getting close to, but can never actually get to. So I can never get to 100% no matter how many I make, because I kind of already started there. So obviously the numbers in the graph are going to determine where that asymptote will be and what's going on. So let's look at a few of these. So we have x squared over x squared plus 1. Notice that if I try to plug in a 0 here, right, I'll add 1, so I'll be okay, I'll still be at 1. If I try to plug in a negative number, like -1, -1 squared is just 1, so we'll be at 2, right? So I can never, ever, x squared plus 1 will never go to 0. If we try to solve, if you notice, it's going to be imaginary where it does become 0. So no value for x will ever make it 0, and you can see there's no jumps, there's no holes, there's no gaps. It just goes. I mean, you can see an asymptote here, right? So it's an imaginary line that the graph is just coming real close to. So how those numbers work together, they're not going to get huge because it's always going to be a fraction, okay? All right, removable discontinuity. So it's not continuous, but removable. So if you think of something that's removable, it can be there or it can't. This is a hole, okay? It's basically when we can cancel out because it's held together by multiplication. So if you notice the graph, it's just like x plus 3 where we have our slope and our y-intercept. But if you look here at -2, you see a hole. X cannot be -2. All right, over here, we have a non-removable discontinuity at 2. So this imaginary line, it's dashed because it's not really a line, okay? So this models the input and the output. This over here models the input and the output also. All right, okay. Woohoo, some more guided notes. Okay, so a removable factor. So those are the things that we can cross off, right? So this is when you cancel out factors. So removable factors in the denominator are holes. So basically if you have something like x plus 2 over x plus 2 times x minus 1, these are excluded values, right? What would make that 0 are excluded values. But because it cancels out, it downgrades to a hole. Okay? And they're called, like we said, removable discontinuities. Okay? Non-removable, so kind of throwing around a lot of the same words. Non-removable factors in the denominator are vertical asymptotes, so those imaginary lines. And are called non-removable discontinuities. So if it can't cancel out, it's non-removable. So I have x plus 1 over x plus 2, non-removable right there. If there are no excluded values, then the graph is continuous. It has no gaps. And you worked with a lot of continuous graphs before, right? When you did linear, when you did quadratic, they went on and on forever, no gaps. Okay, the other skill that you're going to need is you're going to need to find x-intercepts. So what you're going to do to find your x-intercept, just remember an x-intercept is anytime we touch the x-axis. And if you think about the y-axis in comparison, so it's basically when your y is 0. So you're going to set the non-cancelled factors in the numerator, because the denominator controls the gaps, the holes, the asymptotes, but the numerator is going to control where this actually hits the x-axis. So set all non-cancelled factors in the numerator equal to 0 and solve for x. Write it as a coordinate point. All right, for the y-intercept, if you think about a y-intercept, it's when it hits the y-axis, so it's when our x is 0. So all we're going to do is we're just going to evaluate the function when f is 0. So we'll substitute all the x values for 0 and then solve for y. And I'll show you how to do that. And then I'll also show you how to do the domain, but we're going to do it in interval notation. Okay, so here we go. We have this function right here. We're not to the point to graph it yet. We're just going to analyze the domain, points of discontinuity, x and y intercepts. Okay, so point of discontinuity, we're going to factor the denominator so we can see really what's going on there. So this is going to be x minus 3, x minus 1 when I factor that out. So that's what I have going on right there. And so my excluded values are my points of discontinuity. So x cannot be 3 or 1. Now these are both non-removable because they didn't cancel out with anything in the numerator. Okay, so remember, these control my gaps. The top controls a little bit more of what the graph's doing. So my x-intercept, if you remember, just going to focus on the numerator. And if you remember an x-intercept, it's whenever it hits the x-axis, so my y will be 0. So I'm going to take the numerator, set it equal to 0, so we have a y-intercept at 0, or sorry, -3, and the y value is 0. Y-intercept, think about a y-intercept, oops, sorry. If you think about when it hits the y-axis, the y will be a number, and the x will be a 0. So we're going to take this graph, this function, and replace all the x's with 0. Oops. So we have 0 plus 3, 0 minus 0 is 0. We have 3 over 3, which is 1. X is 0, y is 1. Now our domain. So our domain is what x values will work. And so if you think of our excluded values, any value will work except for 3 and 1. So from negative infinity, the smallest number you can think of, negative 1 trillion billion whatever, right? Negative infinity up to 1. And I'm going to skip over 1. So this is just saying, hey, just hop on over 1, right? Go up to 3, hop on over 3, and go to infinity. So we're not including 1 or 3, as you can see there. So our domain does get a little bit crazy. All right, so I want you to try B, C, D, E, and F, and then there will be a video linked if you need to see those. But if you're ready to go for it. If not, watch the next video after you try them.